of ground state of two coupled harmonic oscillator and understood the source of the entanglement, which is basically the coupling constant between two oscillators, K1. Then we generalized it to n coupled harmonic oscillator, and the source of the entanglement was the potential matrix, basically the Kij matrix. And later we generalized it for the free field theory because we wanted to use the n coupled harmonic oscillators. So the configuration was like we have a sphere. Inside the sphere is one subsystem, outside of the sphere is another subsystem, and you put it on a lattice and you quantize the Hamiltonian in the radial direction. And we obtained radially quantized Hamiltonian, which is given in equation 1, where the pi lm are the modes, momentum modes, and the phi lm are the field modes, and r is replaced by I plus half here. And the modes phi and pi satisfy the equal time commutation relation. Now we apply the same procedure what we developed for the n coupled harmonic oscillator. So which is basically you write down the Kij matrix and you just subdivide the Kij matrix A, B, B transpose, and C. You integrate out the first n oscillators or the last n minus n oscillators. It doesn't matter because it's a PO system and SA is same as LP. So you trace out or integrate out the last n minus n sites and evaluate SLM. But you remember that this is for a particular mode L and M. So to obtain the total entanglement, we want us to sum over M and L, right? But if you look at the potential matrix, which comes from the phi I coupling, there is no explicit M dependence in the elements of the matrix. So if you write like K L M Ij phi Lm I phi Lm J, sorry, J, there is no in the matrix element here, the potential matrix, there is no L and H, there is no M dependence in the matrix element. It depends only on the site I and the L. So therefore, when you sum over M and L, that SLM should not depend on the M. So you can sum over M independently, which is 12 plus 1, which you know because M runs from minus L to L. And then you sum from L equals to 0 to infinity.
Sorry, I just have, there is a scratching noise that's coming from somewhere. Is someone's microphone on or? Okay, maybe let's just try again. And, yeah, sorry.
Okay. Okay. So therefore, the entanglement entropy finally becomes this expression, which is sum over L 0 to infinity 12 plus 1 SL. Now you recall the formula we derived for the n-coupled oscillators, where the entanglement entropy was sum over all the eigenvalues corresponding to each oscillators S of zeta I, but the eigenvalues we derived was zeta I to the power n 1 minus zeta I, and finally we get this formula for the n-coupled oscillators. You follow the similar path, the construct KLM matrix again and subdivide the spatial region. And similarly, you will obtain SL as a zeta L 1 minus zeta L log zeta L minus log of 1 minus zeta L. This is the same formula of the n-coupled oscillator, which we derived earlier. Then you finally sum over the M and L to obtain the entanglement entropy. Now we try to establish the area law, which we naively had some argument because I mean since for a pure state SA is same as SB, geometrically it has to be something which is shared by the both, so it should follow the area of the entangling surface. But to prove it, what you do is first you set the radius of the sphere R at a point n plus half, which is midway between an inside point and the outside point. So first n is the inside point of the lattice, and n plus 1 to capital N is the outside point. So you set the radius here, n plus half midway. And you replace R because A is the lattice spacing. R is n plus half A. Now you plot S over R square S versus R square over A square. The plot has been taken from this paper, Entanglement Entropy and Area. And you see it follows a straight line. Here, what has been done numerically is N, the total number of lattice point has been chosen to be 60, and system size, the subsystem size, is varied from 1 to n, 1 to 30. And you plot this S with R squared over A squared, and you get a straight line with a slope 0.3. So this shows that it follows the area law. And you would say, I mean, why? I mean, there could be other terms, and if you just check it, let's say if you want to plot it with R cubed over A cubed, which is you have to plot S over N cubed, S versus N plus half cube, you'll get a number which is significantly smaller than 0.3. So therefore, in the leading order, it follows the area law, and therefore the subleading term. Any question? I can see some ways.
Yeah, Shubham has a question.
Yeah, so the slope is determined by the point from which you decide to sum over, is it?
The slope.
Like
Sorry?
So I was expecting that you would, since this is entanglement entropy, you would sum over some of the lattice points, right? I mean,
Correct. Yeah.
That determines the slope.
Correct. Because I mean, the small is the number of lattice points which you have not traced out.
Right. Well, yeah.
So you are summing over n minus n.
Correct. Yeah, I just wanted to.
Yeah.
Thanks.
So this shows the area law of. I can see another question. Yes.
Yeah. So I didn't catch that last bit about the S versus n plus 1/2 cube, and the coefficient being smaller than 0. I don't understand what that. Can you say that again, please?
So you want to see, I mean, first you want to see whether it follows the area law, the volume law, or something, or any polynomial law. So you first plot it with respect to n plus half square, which goes as the area. Then you want to check it with volume, n plus half cubed. Or if you want to check the linear, n plus half, you plot it with respect to those numbers, right?
Right.
And you check the coefficient of these numbers.
Mm-hmm.
And you say, what is the leading order behavior?
But what is the, what I'm trying to understand is, what is the significance of the coefficient being small or being?
Oh, that tells you what is the leading order behavior.
Yeah, I'm not seeing it somehow. But maybe I don't know. Is it not possible for something to scale with like the volume but have like a small coefficient? Is that not possible? Or I don't know.
Yes, there could be, but that number should be significantly smaller than the area.
Let me understand the question. Are you saying that if, say, suppose whatever the coefficient is, if R is large, then what will happen? Is that the kind of question?
No. R is replaced by n plus half A. So you're plotting basically S with the polynomial of S n plus half to the power, let's say P.
Okay.
And you check for P equals to 0, P equals to 1, P equals to 2 onwards.
Yeah, but say suppose n is okay. In here you have taken to be fixed. Okay, I see.
No, capital N is fixed, but the plot is generated by varying small n.
Then for large n, it would be like whatever the slope is.
There's no large n because you fix the total number of sides, total number of lattice sides.
Okay, I see.
Buddhaditya has a question.
Yeah, so when you're plotting this against other higher powers of n plus half, you won't be getting a straight line, right? So what do you mean by a slope here?
No, I mean, if we are not plotting S versus N, if you plot S versus N plus half to the power P, you would still get a straight line, right?
Okay, I see. I mean,
Because in a like y versus x squared is not a x. I mean, when the curve is y is x squared,
yeah,
when you plot y versus x, it's not a straight line.
yeah,
But when you plot y versus x squared,
yeah. But when you plot y versus x cube, you still don't get a straight line, right?
no, you won't get a straight line.
So that's why I'm saying that when you're plotting against other higher powers of n plus half, you are not getting a straight line, right?
Higher powers.
Yeah, I agree with Buddhaditya. Right. I mean, you are trying to determine the dependence of S on something.
Mhm.
And if you get some straight line with respect to some value of P, why should you get a straight line for other values of P? You should not get, like, you should.
Those will be the other plots, not in the same plot.
Yeah, but those other plots will not be straight. I mean, okay, the point here is that you're trying to determine how the entropy scales, right?
Yeah.
And what you found is that it scales with the area,
Mhm.
right? Which is fine.
Mhm.
But if you plot it against the volume, you're not going to get a straight line.
Yeah.
And I think all that tells you is that entropy does not scale with the volume or with whatever some power p. It does not scale that way.
Okay. Yeah.
So if is this the purpose of this illustration? Because if this is the case, then I agree. Yeah,
Yeah.
this
Yeah.
is fine.
This is the point. This is the point.
Okay. Okay.
Yeah.
All right.
This should be a strong enough argument for this, right? That
Sure. No, I think it's fine at this point. I was just confused about this coefficients and the size of the number in front of it and stuff. That was a bit confusing, but I think it's okay now. Thanks.
Yeah. Thank you.
But later,
So this won't work if you had both the square and the cube in the entropy, for example, right?
sorry. Yeah.
It won't work if you had, say, S scales like R square plus R cube. What would you do then?
R square.
R square by A square plus R cube by A cube, say.
Are you talking about a thermal entropy contribution?
Yeah, I don't know. I mean, you're just checking the entropy. It could be like a polynomial instead of a monomial.
You can determine the polynomial by, I mean, just checking one by one, right? The scaling behavior of the entropy. Why would you expect that it is like R square by A square plus R cubed over A cubed?
But if you're looking for large n, then wouldn't like the highest power always dominate? Means
A large in which n? Capital N or small n?
small n means that's what we are varying, right? Capital N is fixed, small n.
Yeah, but the capital N is fixed. I mean, large n, what does it mean? Sorry. I mean, n cannot exceed capital N. Small n cannot exceed capital N. Because that is the subsystem size.
I mean, the power of N is not changing, right? I mean, that's what Jyotirmoy is perhaps saying, right? I mean,
Yeah.
P is not changing. I mean, of course,
Yeah.
depending on your whatever your system is, N can change. At max, it can become capital N, but
Mhm.
yeah,
The
I
leading
mean,
power, yeah.
so, sorry, Rito, I perhaps didn't understand your question. Yeah, maybe you can.
Yeah, like the question Pawan asked, right? This if it is R square plus R cubed, then like if you want to see want to determine the behavior for larger, I get like the highest power will show up. Means if you plot it by R cube, it will probably give you a straight line. But then for R square, it won't give you a straight line. That's why I thought it was something like that. If you've found that at larger, this behavior is R square over A square, which is the straight line, then you're kind of sure that it will probably go as. It's a follow-up on Pawan's questions.
I'm sorry, I didn't understand the question.
I mean, he is computing S. Now he's just checking against like whatever whether it grows like a R cube or R square. For R square, he's getting that it's a straight line. That should settle the doubt, right? Or no?
Okay, means then like means if you have like a polynomial, how do you say whether it is, means how do you distinguish whether it's a polynomial or a monomial in that, or is it like once you get the straight line it's done?
No, there are subleading correction, of course. I mean, you have to check the other polynomial. I mean, for example, I mean, later, I mean, this was first it was done by Srednicki, the area law checks. Then later, I mean, I have given the UV dependence of the entanglement entropy follows like polynomial law, like r by a squared and so on. And then you would get a term which is a log proportional to the log, and you plot it with a log scale later with the log scale log of n plus half, and you again get a coefficient in front of it.
Sorry.
Yeah, okay, so suppose in this formula you take this a0 r over a square r over a whole square plus c log r log r over a. So in this formula, suppose for the sake of argument you take r to be large, then the first term will dominate and you'll see like area law. That I can understand. But if you come to smaller and smaller r, then you'll find this log behavior also, right? Means similarly, if you have other polynomials, those will also show up kind of.
Correct.
That's what I mean.
No, I mean, so R, I mean, R is of course the varying. Yeah, the small n is varying.
Yeah, right.
Yeah. So you check. I mean, first you check that. I mean, by varying the subsystem size, and you see how each coefficients behave. That is the point.
So the linear plot that you showed, that is exactly, I think, what Ritobroto is saying, that it must be for very high small n, because otherwise you will see the log corrections.
Correct.
Near.
Yeah. Correct.
Okay. Yeah, I think that perhaps was his question, I suppose.
Sorry, but I thought that what is happening is he's taking n going from small n going from 1 to 30, and isn't that what was happening?
Correct. N is varying. Yeah.
So Srednicki's experiment was not able to resolve this or detect this log piece. Is that right?
Correct. That's correct.
So
we just followed the area law. Yeah.
I see. But if you did, let's say, a more sensitive experiment.
Yeah. Which was done, yeah, of course, in this way.
No, I am still a bit confused, because like if you have small n, you can clearly see that the log term will dominate, right? So the plot that you just showed must be for large enough n. Like, I mean, that cannot be, this plot cannot be for small n, right? Because that is given by this log behavior, right?
No, actually small, and first you forget about the log n, because he had no idea about the log behavior.
Okay.
So he was trying to establish the area law first.
Mm-hmm.
Then you vary the subsystem size from just 1 to 30, let's say.
Yeah.
And you try to see what polynomial it behaves.
Mm-hmm.
And he could see it follows the area law because it follows a straight line. That was Srednicki's point.
Like, so on the so where is n in this, like how is there variation with n in this picture?
R x-axis.
R as a function of n, because R is n plus half.
I think this is fine, no, Shubham, because if you look at R square, like close to the origin, there's like a bunch of points just crunched together.
Yeah.
And I don't think this has resolution to kind of determine exactly what is happening.
So I suppose I was saying that, like, this graph can truly be relied on, like, for large enough values of R. Like, I think that's what Ritobroto was also saying.
Yeah, but here n is the x-axis, right? So n can also have value like 0 or very small value.
Mm-hmm.
Sure, it can have, but that this graph, like, you know, this linear fit is probably not correct. Then, I mean, you can of course plot points, but you see from the expression, you see that near the origin, like, it's dominated by log n rather than in square. So the straight line fit is probably not correct at low values of n, like close to the origin.
Right.
That's what I understood, like, from this discussion. Is this correct or wrong? Like,
I also think like that.
Okay.
Yeah. Okay. So the point of the Stradlinski's paper is to establish the area law first. Then later it was corrected. I mean, it's quite involved numerically, and they have got the log weight numerically, and it turned out to be this number, which is near about -1/90 for the massless scalar field in 4 dimensions. But I will show it analytically, this number, the log coefficient of the universal coefficient. My point here was to first show the area law behavior. That's it. Okay. So now I'll start with the path integral formulation of entanglement entropy. So the definition we had given in the last lecture was for the Rayleigh entropy. It was 1/1 minus q log of trace of rho. Now, goal is to first derive the trace of rho. So to define trace of rho, one need the ground state wave function for the field wave. Then you integrate out the subregion and you define rho. The ground state of a ground state wave functional is defined in the following way, which is overlap of phi and psi. Psi is a state, and you integrate over all the phi, and you let time to flow all the way to -infinity. To understand this statement, you go back to path integral quantum mechanics, where we have an overlap of the state at time 0 and capital T, and you see that it becomes x exponential ht and y, and you insert a complete set of eigenbases in the energy state, and you can see the at t equals to -infinity, only the ground state contributes, and you can convince yourself that to obtain the ground state you have to let the time flow all the way to -infinity, and that's how we obtain the ground state of a field theory. Is it okay?
Yeah.
So now you consider 2D slice where time and of course 1D spatial direction. So here the black region denotes the integrated out region, which means you integrate out d phi all the way time -infinity to 0, and the gray is non-integrated one. So it denotes the ground state wave function pictured here, phi psi. To obtain the complex conjugate of that ground state psi star, you have to invert the time. I mean, flip the sign of the time, right? Because psi exponential minus iht and psi star would be the complex conjugate of that. So therefore, the complex conjugate would be the time where Euclidean time flows from 0 to infinity, plus infinity. Okay. So therefore, this is the ground state wave function psi, and it is the complex conjugate of it. So now, when you derive the partition function, which is trace over exponential beta h, where trace is taken over the entire space, right? So therefore, it would be d phi, psi of phi, and psi star of phi x. And remember, it's not a partial trace; it's the entire trace. So therefore, the partition function will be d phi, and psi phi and phi psi. But if you are not familiar with this expression, you can go back again and recall the path integral quantum mechanics, where you derive the partition function in the quantum mechanical way. So you remember the overlap kernel kx1, t1, and x2, t2, which is defined in the following way. Now you weak rotate t1 and t2 and make it Euclidean time.
Jyotirmoy, can you change the color of this font now? It's
Now,
not
no.
really visible.
Yeah.
Blue and
Is
black.
it visible?
I mean, it is for me, but might be a problem for.
Okay.
Okay, so if you can, you can change it.
I mean, do you want the blue one?
Yeah, make it something lighter.
Oh, I mean, I don't know how to change it now.
Okay, it's fine.
Okay. So therefore, the partition function, I mean, the kernel is like x1 overlapped with x2 and exponential of minus h tau. So when you take the trace, it means that you you put x1 is same as x2 and integrate over x1, because that's what the trace means. So therefore, the partition function can be obtained by putting x1 is same as x2 and you integrate over x1. Now you again insert the complete set of eigenbases in an energy eigenbasis, and you obtain phi. I mean, x1 overlapped with n is phi and x1. So therefore, you get integral over dx1 and phi n x1 and phi n star x1. And you again take tau goes to infinity so that the only ground state continues. And finally, you get expression. This is the expression of the partition function because you have taken the trace integral dx1 phi 0 x1 and phi 0 star x1. And now you look at this expression. One can convince yourself this is indeed the expression of the partition function in the field theory. Is it okay? Any question, comment?
Anish, maybe you can ask your question.
Hi, am I audible?
Yeah.
Yeah, sorry, I missed the earlier part of the lecture, so I didn't want to interrupt, but we need not address it if it like slows the flow of the lecture. But so this small n is actually like the if you have like a plane and you're like having a circle separating two subsystems, the small n is the radius of this circle and capital N is the size of the entire system. So as n increases, I mean, people are saying that n, I mean, what about large n? But if n increases to the point that it reaches the size of the system, then entropy should go to 0, right? Because it includes the entire system. So therefore, the linear behavior you cannot see that at large n. It can only be like at whatever. I mean, I don't know what small. It cannot be the size of the system. That's why you have the less than half n or something like that. Not some cutoff like that.
That's a good point. Yeah, entanglement should vanish when n approaches capital N. And precisely he has taken small n to be capital N 60 and he got s to be 0.
Right. Okay.
So then it cannot be too large also, like close
Yeah,
to
yeah.
capital N also. So
Yeah.
it's somewhere, I see. So
that point is mentioned, what you have just said. Yeah. Correct.
Can I make a comment? Like, it is fine to go till half capital N because the complement has the same entropy.
Correct. Because anyway,
So-
it's a pure state. So if you take n to be, let's say, 40, you get SA is same as SB. If you just trace out the first n or the last n minus n, entanglement entropy should be the same.
Yeah, and I guess like there's a lot of chat about this, but I mean, the large and small cap, I mean small and large small n doesn't matter so much because you're comparing 30 squared to log 30. You're comparing 900 to 4 or something. So I mean, it's all fine, I guess. Once you cross 10 or something, you are not going to see the log scaling. You just see the square scaling.
Pratik has a question.
Yeah, so if we increase this n, small n, so we expect that, so as it was earlier said that if we include the entire region, the total entropy should be 0. So do we expect behavior like the page curve here? I mean, first the entropy is increasing, and then after some time it will also decrease, and then total entropy should be 0.
Yeah. Correct. I mean, there is an critical as well.
Okay.
Yeah.
Thank you.
So okay. So we have got the expression for the partition function by tracing out exponential of beta h, and the expression can be justified from the Pareto quantum mechanics. And if you just have an analogy with the quantum mechanics, you can understand this expression. Anyway, now we need a reduced density matrix. Reduced density matrix, I mean, one obtains by integrating out one of the subregions. So here in the spatial slice, you subdivide here tau, of course, in y-axis, and x is the spatial direction. So you subdivide the spatial region by A and B. So this is the A region which is shown in the picture, and the rest is B. So the first task is to divide the sub-region like A and B. Then you obtain the reduced density matrix by integrating out all the fields in the B region in the reduced density matrix, right? That's the definition of the reduced density matrix. You trace it out or integrate out the degrees of freedom present in the other system, other subsystem. So therefore, the reduced density matrix rho A is integrating over the fields over the B region. So therefore, rho A, the expression of the rho A is 1 over z, because you remember it's like trace of exponential beta is divided by that z. So 1 over z, integration of the fields in the B region, and this is the expression of the density matrix phi A phi B in the basis of phi A phi B, phi phi A phi B. You remember that the partition function you have got? Yeah. Now you obtain the reduced density matrix by integrating out the phi B region. And since we are on a single sheet right now, so Z represents the partition function on a single sheet. The 2D plane we have. Then we need to compute, of course, the Rene entropy, and we have to construct trace of rho A to the power q. So you multiply rho A, you prepare q such sheets, 2D planes, and you multiply. The matrix multiplication indicates that you have an alpha beta index of the first matrix, then you have beta gamma. So first beta has to be, this beta has to be same because it's matrix multiplication. And in the last density matrix, rho A has a delta alpha, and this alpha is same as this alpha because there is a big trace sitting outside. Okay. Geometrically, it would imply that the rho A you construct in the first sheet, you connect it with the second sheet because of the matrix multiplication, and second one you connect with the third one, and finally the qth, the last one you have to connect with the first one because there is a big trace sitting outside, which pictorially seems like this. You have first sheet, this is the subregion A, this is subregion B. You connect the first one with the second one with the third one, and finally the last one is connected with the first one. And this has been shown for q equals to 3. And since you want the fields to be continuous, it would force you to put the boundary condition that phi, the field on the ith sheet, has to be same with the i+1 sheet, and finally the qth one, the last one, has to be same with the first one because of the big trace sitting outside. So okay. So therefore the geometry is again.
There's a question.
Hi, Jyotirmoy, can you again go back and say that why do you have different sheets?
Because you have to prepare rho A to the power q, because you want to compute Rene entropy, SAQ. So that is 1 by 1 minus q log of trace of rho A to the power q. When rho A raised to the power q means you multiply rho A q times. Right? When the matrix multiplication would force you like to fix the index, beta is same as beta, this beta, second beta, and since there is a big trace sitting outside, the last index of the matrix rho A, alpha has to be same with the first one. That's the meaning of the trace of the entire.
These are different Riemann sheets, right? Then if these are different Riemann sheets, then why phi is living on the full Riemann plane? Why is it not on a single complex plane?
Why phi? I'm sorry.
The phi, you said the field phi, right?
Yeah, yeah.
After that, then why phi is living on this, not living on a single complex plane rather than living on this full Riemann sheet now? I mean the set of Riemann sheets.
Because you have already constructed rho A to the power q, right? And you want the continuity, right? Of course, the geometry is like this. So you have a radial direction and the angular direction. It's a 2D plane, right?
Right.
2D plane. Now you connect one after another.
Phi is a function of r and tau, right? Initially.
R and tau, correct.
Right. So
Right.
if you don't want to construct, let's say, rho a to the power q, your phi lives on some complex plane, right?
Correct.
Right. Then it's normally if you are extending some complex plane to, I mean, attaching another Riemann sheet to a complex plane, you need some, I mean, these are basically some kind of branch cuts, this gamma alpha, beta gamma, beta alpha kind of things.
Correct.
Why are you having a branch cut on the definition of phi I? That's the question.
So it implies that, I mean, phi is a function of what? I agree. But but it has a periodicity. It is same as r tau plus 2 pi q. I was going to that point. Why I'm saying this, because I mean, when you connect one after another, you forget about the fields conduct. I mean, this is simple geometry first. So you connect one after another, and you get back a single manifold, right? Which is again a 2D manifold.
You're attaching different phis, you mean?
I'm attaching different files, correct? Different sheets.
Okay. Different sheets through this relation. Phi r tau is phi r
plus tau plus 2 pi q, and you get a 2D plane again. But the tau is not. I mean, it doesn't have a 2 pi periodicity because it has. You see, it's a branch cut kind of thing. If you go to 2 pi, if you move,
okay.
You'll go back to the second sheet. And to come back to the first sheet, you have to come back after 2 pi q rotation.
Sure. Okay.
Any questions, comments?
Yeah.
Shubham.
Yeah, but sorry. I mean, your theory in your the theory you started out now is just free scalars, right? I mean,
I haven't specified the field contents yet.
Okay.
I'll do it. I'll define an action on this I mean, conical geometry.
Sorry, then why are we talking about this phi field?
I mean, he asked the question, so I answered it before, but I haven't specified the fields yet.
Okay.
This is just connection of this connection of all the sheets. And if you want to, I mean, if you want to specify any fields on a single sheet on this manifold, on this conical geometry, you have to have this periodicity. That's my point.
Sorry, I'm asking probably very naive questions. Like, where did the branch cut come from? Like, sorry.
No, I mean, I'm giving analogy with the branch cut. Because you know, I mean, when you go to pi periodicity, you don't come back to the same sheet. There is no branch cut, and I mean, I'm giving you the analogy. If you move 2 pi rotation, if you go 2 pi rotation, you go back to another sheet. Remember from the branch cut kind of thing. I mean, then you 4 pi, you go here. The geometry is like that. So if you have a r and tau angle, if you rotate 2 pi, you go on to the second sheet. If you rotate 4 pi, you go on to the third sheet. And after the 2 pi q periodicity, you come back to the original sheet because the last one is connected to the first one.
Okay, you're just simply describing a setup, which we'll explain now, like how it's relevant to evaluating Rayleigh entropy, right?
Yeah.
May I make a comment regarding that? So if I understood correctly, like if suppose you did not have this Q periodicity and if you just had like infinite such copies, then you definitely need a branch cut around this boundary. But because you have this Q periodicity, it's technically just a manifold. Yeah, you just have a weird manifold, but you know it looks like a branch cut if you look at like just 2 sheets or something, but it's not actually a branch cut. This is
I was just giving an analogy.
Right, I understand. Okay.
Nehal had a question.
Yeah, I was going to ask the same question about. So I was thinking when you take q equal to one limit, your branch cut sort of disappears, but that you have already answered that there is no branch. So it's okay.
Okay. Yeah. So the identification of tau is with tau plus 2 pi q, which we have just said. Therefore, trace of rho a to the power q will be integral over all phi b fields because you are preparing phi a, because I mean you are integrating. I can see another raised hand.
Yeah. So I have a question. I think maybe you explained it. I didn't get it. So why is the tau to tau plus 2 pi q identification made?
Yeah, because the last sheet is connected with the first one, correct?
Yeah.
So when you go tau to tau plus 2 pi, you come back, you go on to the second sheet.
So it's like these sheets are connected by rotation in tau.
Connected in rotation in tau. I mean, connected one of
When
the first one is connected with the second one is connected with the third one, but third one is again connected with the first one because there is a big trace sitting outside. That's what I said.
No,
Third
yeah,
one
sure. I got the trace part. I'm just asking that when I'm in my first sheet and I take my tau from, I increase the value of tau by 2 pi, I will go to the second sheet.
Correct.
Right.
Correct.
Okay. I see. Okay. Thank you.
So now you want to evaluate trace of rho a to the power q. So therefore, you have to multiply the rho a q times and take a whole trace sitting outside, which is shown pictorially here. And you see there is a 1 over z sitting outside because from the definition of the rho a, you see rho a has a 1 over z integral over d phi b, phi b phi phi b, and you multiply it q times. So therefore, rho a to the power q becomes 1 over z to the power q, where z is a partition function on a single sheet. And you take the whole trace. And if you look at the expression of the partition function, you would get finally multiplication of this thing q times, where phi is a phi b, because b region is only integrated over. Therefore, you can write trace of rho a to the power q, trace of rho a to the power q as a partition function on this q fold cover divided by partition function on a single sheet raised to the power q. Is it okay?
Can you please, can you please repeat that argument?
Okay, so you look at the expression of the trace of rho a first. It's rho a. Expression of the rho a. Rho a. You look at the expression of the rho a. 1 over z d phi b integration of the region d and this object. Now you prepare rho a to the power q. Therefore, you have to multiply the same object b times, q times, and the region b is integrated over. When you multiply q such times, this has an index alpha beta. Then another copy you would have a beta gamma and so on. And finally, you have a gamma alpha, which matches with this one. And the phi field is integrated over the entire B region of the connection, Q-fold connection. Is it okay?
Yeah, it's fine. Thanks.
Yeah.
So you're saying there's only one phi b integration?
One phi, because you have joined the phi, right? I mean the sheets. Therefore, field has to be continued, right?
Okay.
I can see another way now.
Yeah, so I just have one more small question about the periodicity of the tau. So usually periodicity of the Euclidean time is related to the temperature, right?
Correct. We'll come back to it. I mean, yeah. You can ask, yeah. Yeah,
Okay,
go on. Please,
no, I'm just asking what's the connection here with Q and
let me answer it. So this partition function is indeed, I mean, when you have a periodicity in Euclidean time direction, this partition function is indeed a partition function of thermal ensemble, which we'll identify later, third or fourth lecture. Correct.
Okay.
So therefore, Therefore, the Rene entropy, I mean, we have obtained the trace of rho a to the power q, which is 1 over z1 to the, 1 over z1 to the power q multiplied with zq, where the zq is the partition function of the q-fold cover, and z1 is the partition function on a single sheet. Now you want to compute the SQ, the Rene entropy, which is 1 by 1 minus q log of trace of rho a to the power q. You plug it back, and you end up getting an expression like this: 1 by 1 minus q log zq minus q log z1. So finally, the Rene entropy has has become a function of the partition function of this Q fold cover. So the task is to compute the partition function of this Q fold cover. Correct? It's a log Z. Now what I'll do is I'll compute this partition function for scalar field or conformal scalar field. Scalar field in 2 dimensions. But I'll take a slightly different approach. So I'll map this thing on sphere. So the coordinate transformation I'll use x1 equals to sine theta, x2 equals to cos theta, cos theta. And remember, the metric was
Phil has a question, maybe.
What?
Hi, so this is something I tried to ask you yesterday also. So, like in the corners of the slit, the edges of, at the endpoints of the slit, it seems there is some singular kind of behavior, right? You have to kind of identify and so on. So when you do this very carefully in field theory, I don't usually hear anyone talking about this. That shouldn't you really be imposing some extra boundary conditions at the end of the slit?
End of the slit means, of region A or B?
At the boundary of the line segments. A and B are line segments. There are boundaries of line segments where you end up having to, like, just because you want some regular behavior, you will have to impose some nice conditions, right? Like continuity or whatever. So
but this division is imaginary, right? We are not just dividing and fixing. It is imaginary. You imagine that A is, phi is phi, right? And phi at region A and near about the boundary. Near about the boundary has to be same as phi at the region B, near about the boundary.
What do you mean imaginary? Because you're literally doing path integral on a n-fold cover.
Yeah. The division, the subdivision is imaginary. You divide it. You imagine that regions are subdivided in the following way. That's what I mean.
Okay, thanks.
But somehow we get the partition function. The entropy as a function of the partition function. So, now we have to compute the partition function. The subdivision and subsystems somehow disappeared, and not disappeared. They are implicit, but this is the expression we got. Okay. Yeah, the metric on that conifold geometry you got was dr squared plus r squared d tau squared, because it's a 2D sheet, but tau is identified with tau plus 2 pi q. Now I use the coordinate transformation. X1 equals to sine theta, x2 equals to cos theta cos tau, and x3 equals to cos theta sine tau, with the condition x1 squared plus x2 squared plus x3 squared equals to 1. Now you do dA squared, you end up getting d theta squared plus theta d tau squared. This tau is the same tau which we identified earlier. Therefore, if you now, this is our sphere metric, but tau is identified with tau plus 2 pi q. Therefore, it's called the branched sphere S2q, because our sphere S2 metric, which is like simple d theta square plus sine square theta d phi square. You can get back this by substituting theta by theta pi by 2 minus theta. Correct? This is the same one. But this tau is identified with tau plus 2 pi q now. So therefore, it doesn't have a 2 pi periodicity like we had in phi. So azimuthal angle, if you give a 2 pi periodicity, you come back to the same point. But here you have to go 2 pi q rotation to come back to the same point. So that's why it's called the branch. Okay. So this is the mapping of that sheet onto the sphere. Now you have to evaluate the partition function on the sphere. Okay, now ZQ has been mapped on the sphere. Evaluate log ZQ. So
Anish has a question.
Yeah, sorry. Can you, so just from the can you show that n-fold cover once more? I just want to understand the coordinate system. So this n-fold cover. Each plane. Let's say, what is the dimensionality of that? Is it R2 or R3 or?
This is R2 at a constant axis. This is R2.
So this is R2. Okay. So now this n-fold cover is also two-dimensional, right?
Right.
What does this x3 then mean? You're embedding somehow this.
Embedding somehow, and I have imposed the constraint like x1 square plus x2 square plus x3 square is 1.
So okay, so this is some weird manifold, right? Because of this n-fold cover nature. So it's not necessarily possible to embed this in R3. You might need some higher dimensional space to embed this. But you're trying to embed this in R3, and therefore you have this 2 pi periodicity that you're ending up with this the metric that you're writing down, this d theta square. So this in principle should cover only the single plane. But you are somehow saying that I'm using the same copy of this metric for all planes.
Yeah. Because I mean, the way I have defined, because the tau has been the same tau,
right?
And the tau had a periodicity, you remember, in that conical geometry. So therefore, it implies the same thing in the branched version.
Right, but if I just say cos theta is theta plus 2 pi, I mean, I just do it. If I just do, I see. Okay, so the periodicity is in theta.
Oh.
Okay, I understand. Okay. Okay, yeah.
Yeah, my point was to calculate the partition function of conformal scalar on a branch sphere. So you start with the while invariant action, because we want to do for the conformal scalar. The while invariant action is given for arbitrary. First, let's write down the arbitrary, then I'll come back to do del mu phi plus. So you can ask that, yeah, I could have started with del mu phi only. But if you compute the stress tensor with the del mu phi, you get del mu phi. And the while invariance tells you immediate consequence of the while invariance is the stresslessness of the stressness. I'll show how. So the while invariance is defined chi mu nu omega square function of x. Chi mu nu t by x. Therefore, you write omega squared as exponential phi, or it becomes exponential. Omega is exponential phi. Therefore, that becomes exponential 2 pi g mu nu x. Therefore, delta g mu nu, write it as 2 pi g mu nu, because if you expand exponential to 2 pi is 1 plus 2 pi. So now you want to see what happens of the action under the while invariance. So delta S under the while transformation, you can write del S del G mu nu, del G mu nu. And you remember the definition of the stress tensor, that stress tensor is proportional to del S del G mu nu. The definition was so you can write down as T mu nu delta G mu nu. And delta G mu nu is proportional to G mu nu. Therefore, it's nothing but the trace of the stress tensor. Now you demand that action is invariant under the while transformation, which means that delta is 0. Therefore, the immediate consequence is that the tracelessness of the stress tensor. But if you start with the del mu phi action, you get this stress tensor. I mean, if you can see in here, And therefore the stress tensor, the trace of the stress tensor will be del phi squared minus d by 2 del phi squared. And you can see the trace doesn't vanish for arbitrary d greater than 2. It vanishes only when d is same as 2, d equals 2. Therefore, you need to add a term which is the curvature coupled mass term, zeta or phi squared, and you compute del S del G mu nu or the stress tensor, Q mu nu, and you demand the tracelessness of the stress tensor, and which fixes the zeta value. So what you do is you have an action which is while invariant ddx root g del mu phi plus zeta r phi squared. You compute stress tensor and demand the trace to be 0. That will fix the value of zeta. I'm giving you the value of zeta is given by t minus 2, 4, t minus 2. See, in d equals to 2, as I have said, d equals to 2, trace automatically vanishes. And therefore, you don't need the zeta or the curvature coupling. So you can, for the 2D, you can start with the action d2x. For 2D, you can start with an action d2x, then mu phi, and that is good enough. And it says that any 2D matrix is conformally equivalent to a flat matrix.
Anish has a question.
Yeah.
Yeah, so this is a more basic question is that, so when you have minimally coupled theories, the stress tensor is defined by the variation of the matter part of the action with respect to the metric. When you have conformally coupled theories, you just vary the entire action. I mean, what is the definition?
Matter part of it.
So how do you distinguish what is the matter part of it in conformally coupled theories?
I mean, you have a phi which is coupled with the gravity.
Right. I mean, see, in minimally coupled, you have a decomposition as a sum, right? Like, you know, S gravity plus S matter. But here, it's not like that kind of, you have R times phi square. Like, you have some sort of product. So what is...
so it is S gravity you forget about. This is the S matter only.
But what is S gravity? That's my question.
It is an Einstein gravity. I mean, R is just S2 metric. That's Einstein specific.
Sorry, can you repeat that? I couldn't hear you.
I mean, there is S gravity. I mean, you can think of there is S gravity, but we are talking about.
Sorry, I mean, this Anish, like this is like the definition of stress tensor, right? Delta is 2 over square root g delta is delta g mu nu.
That is the definition provided S is H matter, right? Because if S is
matter,
like
why?
So
I mean,
you need to separate out the gravitational part, and whatever is left over, you do that.
I mean, gravity part is the Einstein gravity action. That is not written here. This is the matter part of the action.
Okay, maybe it's a very naive question, but see, if I had R plus del mu phi,
R plus
like the usual R, like the Einstein-Hilbert term plus the matter part, then the delta S gravity is just the integral over R, and the delta S matter is whatever is left over. And then this definition is fine. But if I have R times phi square, so then how do I separate what is gravitational? I mean, do I just consider R phi square itself the entirety as the gravitational term? That's my question.
No, R is no, R minus 2 lambda is separated out. This is the curvature coupling with the matter part. It's already been separated out. You don't have to the gravity. We have to separate out the gravity and the matter later.
I see. So you already have, okay. I see. I thought this was the entire action. Okay.
No. It has already been separated out. And and I have used the definition of the stress tensor, but I mean, when I write the stress tensor in the polynomial, it means that action is the matter action.
Okay. I see. Okay.
I mean, you are doing everything for a CFT, right?
Correct.
So in CFT, I thought like there was no like separating out matter part or gravity part.
No,
I mean,
I'm just giving the example of the while invariant first.
I see. So you just have a background geometry that is while invariant, or
no, this is I'm saying the action of while invariant. I'm just is a side thing. While invariant action in arbitrary dimension, but we are on S2. Right?
Okay.
I'll come back to the S2. The action will be just root G d2x del mu phi del mu phi. That's it. Is it okay? Because that's the while invariant action you have in two-dimensional space. Because we are dealing with a conformal scalar. Is it okay?
Yeah.
So why I'm doing this? Because I need to evaluate the partition function ultimately on the S2Q, the branch sphere, right? So therefore, the action is given like root G d2x del mu phi del mu phi, and there is a half sigma outside, of course. The partition function is written as d phi exponential of minus s, right? D phi. You plug that action minus half root G d2x del mu phi del mu phi. Now you perform one integration by parts, you bring it here, and finally you get a Gaussian in phi with a scalar Laplacian. Correct? Therefore, you get a partition function which would be 1 over square root of determinant of spin zero Laplacian on S2. Is it okay? The expression of the partition function. Any questions, comment?
So when you're writing this as 1 over square root of a determinant, here you are neglecting the zero modes, right? Of the Laplacian.
No, the zero. Neglecting the zero mode because because you're saying because the zero modes are not exponentially separate. You would end up getting
means you'll get a divergent basically.
Yeah, you would get a divergent because the integral over d phi will be only integral.
Typically, people treat it like separately.
Yeah, I'll treat this separately for the gauge thing. For the scalar, I'm just taking it. You imagine n equals to 0 is separated out.
Jyotirmoy, you have half an hour left.
Okay. Therefore,
So do you want to take more questions? Or
yeah, it's okay.
do you want to finish some?
Yeah, okay. Go on.
Akhil had a question, yeah.
I missed again. Like, did you say we are in 2D only and right? And
yeah.
and what is this x2 power q again? Like, if it's
not
2D,
power, it's q is denoted with a branched line. It's not 2D sphere because one of the angle has a 2 pi q periodicity. That q is denoted by this. It's not raised q, it's just notation.
Can I make a comment on that? So what essentially, like, suppose you just had a plane, you can like add R2, you can coordinatize with a single S2, right? So then you have a d theta and a d phi coordinate. The phi, so you have a d theta plus whatever sine or cos depending on origin, and then a d phi square. Now this will cover the cover an S2, but it's like the origin is ill-defined, whichever. Okay. Now what he's saying is that now if instead of keeping phi periodic about 2 pi, you make the periodicity 2 pi q. So this is like a sphere, but because the phi coordinate has this 2 pi q periodicity, it's like a whatever branch sphere, whatever they call it, and that is denoting by this S2q. Does that answer?
Yeah, that's what I said. I also explained S2q what it means.
Right.
Yeah, that part is kind of fine. Like, I got slightly confused because the n-fold picture we had was only for the spatial surface, right?
On the spatial surface, it is also a spatial surface.
So now I'm confused whether like should the picture of the n-fold cover we drew was only for the spatial part, right? It didn't have any time in it. Is that right?
I mean, we always take at a constant time place. Those like sheets were also prepared at a constant time space.
Right. So sheets were prepared at a constant time space, and that had a branched behavior. But now the whole theory is in a 2-dimension, right? Maybe I'm asking something stupid. So
no, you go on.
So now the branch is on a full Euclidean thing, which is 2D.
What I have done is you had prepared and I had prepared few such sheets then you got a Q fold cover, and I mapped that cover under coordinate transformation onto a sphere. But because you had a periodicity 2 pi q in that cover and on the sheet, you get 2 pi q periodicity on the azimuthal angle of the sphere, and it is called the branch sphere because it doesn't have a 2 pi periodicity.
My confusion is this: we are doing a calculation on a time slice, right?
Correct.
But you also said that 3D should be 2D because you wanted conformal invariance without the psi term, correct?
Correct.
So now if you're on a time slice in a 2D surface, what are these 2 dimensions? I'm slightly confused.
Now I mean the partition function is on 2D space. That ZQ, what you had prepared ZQ final expression, that was on 2D space. Correct?
That was because I thought we had a 3D theory. No,
because we had used the embedding space, right, with an x3 coordinate, and they had a constraint.
Oh, right. So now okay, we are in some embedding space. Okay, thank you.
So therefore, the partition function is 1 by square root of determinant of spin zero Laplacian on transfer S to Q. Therefore, log ZQ minus half of log determinant of spin zero Laplacian.
I think the audio is fainter now.
Audio?
Yeah, can you be? I think you became farther away from your mic or something. For me, the volume is low.
Okay.
Is it the same for others?
Okay, I'll speak loudly. Is it okay?
Yeah, no, perfect.
Great. So now you use log of determinant as a trace of log. This identity from linear algebra, trace of log of delta C. Now you use log of, I'm using an identity. Log of y is written 0 to infinity t tau over tau exponential of minus tau minus exponential of minus tau. Try to prove it. I'm giving you the hints. So it can be expressed in terms of the exponential integral. Set to infinity exponential of dz over t dt, and the expansion in series around z equals to 0 as a gamma minus log z minus 1 to infinity. So using these two these two properties, you try to prove the log y can be written in terms of in the following integral transformation. Now I just substitute this integral here. So therefore, I can write log of zq equals to 0 to infinity. There is a half sitting outside. So d tau over 2 tau. Trace is always there. Exponential minus t box 0 minus exponential of t. Is it okay? Good. Now what you have to evaluate is a trace of this operator. So the eigenvalue and the degeneracy is given on the branch sphere. I'm taking it as data. Lambda n plus n over q times n plus n over q plus 1. Now we note that for q equals to 1, you come back to your original, our ordinary sphere. So you can replace n plus m when q equals to 1. You can replace n plus m with another integer l, and you end up getting l into l plus 1.
Shubham has a question.
So how did you? I mean, these are well known.
Yeah, these are, this eigenvalue and degeneracy, you have to compute it by just solving the Laplacian on sphere, the branch sphere. On the branch sphere, and you put a boundary condition of the eigenfunction, the way we do it for the ordinary sphere. But I'm not going to do it, but I'll take it as data. I'm giving you the source and the degeneracy, of course. For the arbitrary dimension, it is n when m equals to 0. There are two integers because of the branching. When m equals to 0, it is n plus t minus 2. Choose t minus 2. And when m greater than 0, it's twice of that. This can be found so I'm taking this as a data to write down the partition function. I'm not going to do it because you have to solve the Laplacian on the branch square, like we do it for the hydrogen atom on spherical surfaces, spherical wave functions. So now I'm writing down the partition function log of set q. 0 to infinity d tau over 2 tau sum over, because there is a trace, so the sum over degeneracy in exponential of tau lambda n minus exponential of tau. Now I have replaced the delta 0 by their eigenvalues and trace by the sum over the sum over nm degeneracy gn, because each eigenvalue is weighted with a particular degeneracy factor. Okay, this step is okay. Any question, comment? Okay. How much time do I have?
20 minutes.
20 minutes. Okay.
In this problem, we are at d equal to 2, right? Or
yeah, d equals to 2. You substitute d equals to 2 here. I'm giving you the general formula for arbitrary. You can, so you can substitute d equal to 2 to get the
d equal to 2 is just 1. The degeneracy will be just
1 and 2. Yeah, for m equals to
1 and 2,
1.
right?
Yeah.
Right.
Okay. So you have two terms. The first term is this, second term is this. Now let's look at the second term first, where you have to do sum over degeneracy. GNM. Okay. Now the way one performs this, because GNM is a polynomial, how do you, and NM all runs from 0 to infinity. Now how would you do this summation? You have to either zeta regularize, because GNM is simple polynomial, because it can see from the expression, and you have to regularize it by zeta regularization or some other regularization method, correct? Because it appears to be infinite at the first place. So what you do is, first you take the expression of the GNM, you use a regulator by exponential minus an, and you perform the sum, and you get some expression FAN, because you see GNM doesn't have an M dependence. Now you expand it in Taylor series and collect the term which is A independent or regulator independent. And that's how we also do the sum over n, I guess. I mean, the first, that's how we also use the zeta regularization prescription, the sum over n. And I mean, I'm collecting the A independent term because it is, because that's how the regulator, it's the regulator independent term. Okay, any question here? Is it convincing, the regularization prescription? Okay, and A independent term turns out to be 0. You can do it. I request you to do it. I've given you GNM, and you perform this sum because there is exponential regulator, and you Taylor expanding about A equals to 0. And this is convergent, and the value is 0. So therefore, you can neglect the second term and start with the first term and proceed with the first term. So now set q is 0 to infinity d tau over 2 tau sum over n g n m exponential tau lambda n. Now we look at the expression of the lambda n. It's quadratic in n and n. And this sum is not easy to perform because whenever you have it, the geometric sum is easy when you have e to the power ax or an, right? An. But if you have an squared, you can try. It's hard, right? So you have to. I will follow some techniques. How much time I have? 15 minutes. I don't think I'll be able to cover it completely, but let me just write down for a while. So we have theta sum over nm gnm. You first complete the square of the lambda n. So lambda n expression, you know, n plus m by q plus 1 times n. Yeah, you can write it n plus m by q n plus m by q the whole squared minus 1/4. Okay. Now I'll introduce another regulator. I have introduced the epsilon in the expression, and at the end of the calculation, I'll take epsilon goes to 0. Is it okay? This step?
Yeah.
Okay. Yeah. Now, I think it will involve, I mean, there is some calculation involved, which I'll not be able to finish it in 10, 12 minutes. But let me stop it here and discuss what we have done so far. Okay. And take some questions. So we have started out the expression of the entropy, which is log of zq minus q log z1. Now our task is to compute the log of zq. That's what we are doing. So finally, for the conformal scalar, finally we get action for the conformal scalar in 2 dimension, and we are evaluating the partition function for the 2D scalar on a sphere which is branched delta 0. The identity we have used is the following to evaluate log y is d tau over tau exponential of minus tau minus y tau. Now you use y as a delta 0 and you perform the steps which I have given. Sometimes it's also called the hit kernel procedure, but it is the way it is. And what you would need to evaluate the trace and the determinant or exponential trace, the trace of exponential of the operator, you would need the eigenvalue, degeneracy, which I have taken it, and you perform the log of zq. Finally, we end up getting an expression of log of zq, which looks like an integral transformation of the degeneracy and the eigenvalue, exponential of the eigenvalue, with d tau over 2 tau with a regulated exponential of epsilon square over 4 tau. Okay. Yeah, I'll stop it here for today. And if there is a question, comment, I can take. Question.
Yeah.
No, I was clapping.
So I think people have seen this derivation in terms of twist operator or something, but I didn't want to go in that way because I have to generalize it for arbitrary dimension. So I have taken this path. I don't think anybody has seen this derivation. This is one loop, the computation of the one loop partition function, and this has been developed quite recently by I should mention the paper. It's by Tenef et al. It came in 2020 October. I forgot the archive number. I'll mention it. Okay, any steps? If any step is not clear, please let me know.
Just one small this thing, just like a minor. So this should be n plus m by q plus half whole square minus 1/4.
Is it half? So okay.
So if you just complete the square.
Yeah. Let me just see. N plus m q. Sorry. N plus m by q plus 1. So you have n plus m by q whole square plus 2 n plus m by q and so plus half whole square minus half whole square, correct?
Yeah.
So therefore, there is a half, correct? There is a half. Thanks. So you can see the generalization to arbitrary dimension is the same. So you have, in the n sheet cover, you have the other dimension, which is now for 2D is compressed onto a sheet. And the generalization would be d-dimensional branched pair. And I'll use the same eigenvalue and the degeneracy which I have given for the d dimension. So the generalization is quite simple in this way.
But like the t mu will, the trace of the t mu will not be 0 in higher dimension.
Correct.
That you
Yeah. Then you have to
so
fix
that
the
doesn't
theta.
affect.
Then what you for the d dimension, the action is del mu phi and zeta r phi squared. Then you have to demand the tracelessness, which will fix the zeta.
Okay. I see. Okay.
Therefore, it is not a massless scalar in the higher dimension. It is a curvature. It has a mass which is curvature, which comes from the curvature coupling.
Okay, I see.
Although it's, there is no m square phi square in to start with. M is when we introduce m as a parameter. But this
you wanted a conformally coupled scale.
Correct.
Right?
That's the point. You have to have a curvature coupled mass to make the trace of the stress tensor to be 0.
Thank you.
Any other point?
So if there are no further questions, maybe you can pause the recording and our discussion can be continued then.